artificial intelligence capable cognitive radio Vandermonde subspace frequency division multiplexing unified globalist standard. With an increase in frequency, different human skin models show the same results. Penetration depth of exposure decreases as frequency goes up. At 60 gigahertz, 34 to 42% of any power is reflected away from the skin. It's a frequency range that's high enough that it's starting to behave like infrared energy or light. It bounces off of things. And whatever tries to get through can't get past 3 millimeters unless you really jack up the energy levels. Extremely high frequency is the International Telecommunications Union's, ITU, designation for the band below the extremely low infrared frequencies in light and above the super high frequency band and this is called EHF. The 1 millimeter band, which is a portion of this, is part of the microwave radio spectrum internationally allocated to amateur radio and amateur satellite use and a few other incidental things and various processes. I'll explain why. This band is considered to be between 241 gigahertz and 250 gigahertz for the amateur satellite band and amateur radio. Amateurs operate on a primary basis between 248 gigahertz and 250 gigahertz, and a secondary basis in the rest of the band. The 57 to 64 gigahertz region is subject to resonance with oxygen in the air and is severely attenuated. In climates other than deserts, absorption due to humidity also affects propagation, and rain fade is an extreme problem. This short wavelength does allow modest-sized antennas to have a small beam width, further increasing frequency reuse potential by making point-to-point or pinpoint accurate communications signals go through, even with very simplified antennas. And because the signal is attenuated like this, it does the opposite of what you think radio would do. It doesn't go very far. From 30, here we go, sorry, reading the wrong line. The 71 to 76, 81 to 86, and 82 to 95 gigahertz bands are also used for point-to-point high bandwidth communication links. These higher frequencies do not suffer from oxygen absorption at those points, but require transmitter licenses in the U.S. from the Federal Communications Commission for doing up and down link. From 30 to 300 gigahertz, radio waves in this band have high atmospheric attenuation in any way and are absorbed by the gases in the atmosphere, almost all of them. They're blocked by building walls and attenuated by plants. Therefore, they have short range, can only be used for around a kilometer, maybe 2 at the extreme. They're good for terrestrial communication and line of sight, as they show optical propagation characteristics and can be reflected and focused by small metal surfaces around a foot across. So you can use really, really tiny satellite dish looking things. And they suffer from another problem, Doppler shift. Even a person walking will distort the signal. We seem to have more effect on it than it has on the 33.4 to 36 gigahertz K-band is used for speed detecting radar guns. The 40 to 70 gigahertz corresponds to wavelengths of 7.5 and 4.3 millimeter. But this is not like the Raytheon 3 millimeter wavelength active denial system that causes pain, which uses an insane amount of energy, by the way. Why am I bringing up all of this stuff? Well, here we go. The Federal Communications Commission is streamlining approval of the 5G network due to its new and much smaller and lower power cell tower usage potential. Since you have to put them closer together, the FCC requirement, since they can't interfere with each other even by accident, is to run them at even lower power output. and make this maybe the dominant characteristic because of the insane bandwidth capability. It's just worthless by normal radio standards because it doesn't work more than 3,000 feet most of the time. But it has a high signal-to-noise ratio. There's almost no noise in those frequencies. This should be considered to be done with our consent because everybody complains about cell towers being too powerful and being able to penetrate skin into the brain. Zero concern for safety since it can't get in more than 3 millimeters no matter what the hell you do, and it bounces off skin. Your skin is a radio reflector. Non-experimental 28 gigahertz to 100 gigahertz frequencies with extensive safety testing just simply because they did them, because they were curious about them, and almost nobody sitting around propagandizing it. What a giant threat to RF phobics, to radio frequency phobics, and people who scream that the FCC is out to get you, to find out that there's an entire group of bandwidths that are the polar opposite of the thing they complain about. Most of the signal bounces off of skin. It can't go in more than 3 millimeters even if you push it. Now we're going to do the other part of this, if I can get to it real quick here. Penetration depth in human skin goes from being maybe 6 millimeters at 10 gigahertz down to 1 millimeter or 2 millimeters at 20 gigahertz, just by doubling the frequency. At triple that, it's at 1 millimeter or less in many cases. It just can't get any further. Temperatures. Now this is based on temperature changes of 1/1000th of a degree Celsius over surface areas of 3 layers of human tissue models at depth millimeters. 35 millimeters maximum depth no matter what the hell you do with it, and that's it. It just tops out. It's like a cutoff point. It looks like a diode switch. Next, energy levels that are considered of concern in any frequency range, immediately divide it by 10 or more because it won't go any further. So everything basically above 30 gigahertz is safer, has no ability to go in, and bounces off of humans or cats. Beware the cats. Next, quiz question. If you're told that 100 thousandths of a watt over a square centimeter is a hazardous level of energy, how do you multiply that out for a human surface area of a body? Well, human beings, apparently, on surface area, if you were to get the entire body hit with it, is about 2 square meters. Let's just say that for skin. Okay, how many square centimeters in a square meter, and multiply it by 2? How much energy, total wattage, would you have to hit somebody with for it to be considered hazardous? I'll include a link in the description to the image I'm going to be using also for the thumbnail, and it includes that off to the side as a little off-the-side thing. And is that a hazard for humans, or is it the hazard level for energy output for electronics? You might want to go look up where I got it from. Thanks for watching. Have a good day.